Today we're going to be looking at the idea of even and odd functions where they talk about symmetry. An even function is called an even function a lot of times because of its exponents, but there are also specialized types such as absolute value and things like that that really don't have exponents, so we have to go a little further than that. Now, an even function is specifically one that has y-axis symmetry. Like we see pictured. So if we look at function g of x, we can see that it has y-axis symmetry. If I pick some value of x, I'm just going to call that x, as an ordered pair, that would be x. And then we'd fill that in, we'd get the y value. So if that were 4, we'd have g of 4. If that were 7, we'd have g of 7. So I can think of this y value as g of x. Now to investigate this, if I pick a value that's exactly x units in the opposite direction, I could call that negative x. So this ordered pair right here would be negative x, and its y value would be g of negative x. So when we compare with even functions, we can find that g of x is exactly equal to g of negative x, meaning the y values are the same at x and negative x. The y values are the same at 2 and negative 2, 3 and negative 3, etc. So in order to show this and not assume anything from the graph, I can do an algebraic test. Now our algebraic test is simply trying to determine, is g of x equal to g of negative x? Well, we know what g of x is. G of x is x to the 4th plus 3x squared. So I don't have to do anything special with that. I can figure out what g of negative x is by doing a substitution. Every time I see an x in this function, I'm going to replace it with negative x. Now, I'm going to simplify completely on that right side. So if I take negative x to the 4th power, I'll take negative x times negative x times negative x times negative x. I will get a positive x to the 4th. If I take negative x and square it, I'll have negative x times negative x, which is a positive x squared, times a positive 3 would be a positive 3x squared. So when I compare g of x to g of negative x, the question is, are they exactly the same? They are, so therefore g of x is equal to g of negative x, since g of x is equal to g of negative x, then it is an even function with y-axis symmetry. The same idea is going to hold an odd function. So here, an odd function you might expect to have odd exponents. And so we have x cubed, that's an odd number. X to the 1st, that's an odd number. So I'm going to think this is an odd exponent, or an odd function. If I graph this, we find that when we compare an x, there's our x, and our y value would be g of x. When I pick a point over here at negative x, exactly x units the other direction, I find this ordered pair up here. So my ordered pair can be written as negative x and g of negative x. So when I compare this ordered pair, xg of x, to this ordered pair, negative x, g of negative x, I'm really concerned, how do the y values compare? Well, the y values are not the same like they were on an even function. They're exactly opposites. So I can't say, excuse the bell, I can't say that g of x is equal to g of negative x like the last function, but I can say that they are opposites of each other. So g of negative x is the opposite of g of positive x. So they had to be exactly opposite all the way through, which leads me to the algebraic test. The algebraic test, basically I'm going to take my h of x and I'm going to compare it to h of negative x. And when I substitute in negative x every time I see the variable, and I simplify, I'll have, in this case, negative x times negative x times negative x, which is a negative x cubed, times a negative 2 is a positive 2x cubed. When I take a negative x times a negative, or the opposite of negative x like we have here, that would become a plus x. Now I'm going to compare, like before, h of x to h of negative x. We don't find that they're exactly the same, we find they're exactly opposites. So I can reach a conclusion, since h of x is the opposite of h of negative x, then it is an odd function with what's called origin symmetry, which is a rotation around the origin. So that's our test for an odd function. We have a mixture of those. If you perform an algebraic test on a function and it does not yield even or odd, then it's classified as neither, and it's not going to have any symmetry. Okay, keep in mind we're talking about a function. So, for example, I'm just going to make something up. If I have k of x equals 3 times the absolute value of x minus 2x to the fifth, and I want to see if it's even or odd or neither, I'm going to do k of negative x just like before. I'm going to simplify. So absolute value of negative x, I want to see how that compares. I know the absolute value of 2 and absolute value of negative 2 are exactly the same. So I can say the absolute value of negative x, therefore, is the same thing as the absolute value of positive x, which is kind of my goal, is to compare those two. So that makes them equal. So far it looks like it's even. But when I simplify this quantity, negative x times negative x 5 factors times a negative 2, well, the negative x to the fifth is going to be negative, times a negative is going to be a positive 2x to the fifth. So here, when we compare k of x to k of negative x, they're not exactly the same, so they're not even. They're not exactly opposites, so they're not odd. So therefore, we can say it is neither even or odd and has no symmetry. So, quick examples of our lesson today. If you need additional support, you can look on YouTube for some additional ones on even and odd functions, and you could also check my channel.